Hello, my name is Jeff Dalgleish. I'm the CTO at Data Squared. I'd like to take you on a walkthrough of our platform and how we've used it to solve a use case regarding cybersecurity. So just to kind of give you a sense of what a linked data platform is, which is what reView is, I like this quote by Tim. He talks about one of the biggest common challenges in large organizations today are data silos, which everyone's aware of, and we know that that's something that we want to break down, but how you go about doing that's sometimes elusive. What we do is we're breaking down data silos by semantically connecting data together into a knowledge graph. And we look at the data and we understand what its connective tissue is. How does one idea relate to another? How does one person relate to different evidence? How does different evidence relate to different people? All of these connections and how things are related are incredibly important when working with large language models and using them to reason over data. At a high level, there's sort of 5 main reasons why you would want to use a linked data platform. One is integration. You can integrate your data between a whole bunch of different systems and departments. It's very easy to do that. The context gets preserved. Instead of just having rows and columns in a database, we have people and organizations and all of these semantically rich relationships. Discoverability. It makes it easy to find information because it's really in one big knowledge model. Flexibility is important because as you find new information, you want that model to change and you want new information to be incorporated. And I'll show you how we did that in this use case. And of course, scalability. These systems need to be able to handle massive amounts of data, and these linked data platforms are very good at scaling. We use Neo4j as our underlying graph database, and it has an amazing ability to scale. So let's talk about how do we do this? How do we take private data and turn it into linked data? Well, first I'll give you an idea of what we're doing as a process. So we're using large language models, and the way they're created is they take public data. We don't create the large language models. We just use all of the ones that are available out there, including private ones that people may have custom trained as well. But basically there's public data that runs through these transformer mechanisms, and it creates these models, which are language models, large language models with billions of parameters in them. And it allows us to do question answering that most people are familiar with. But what we want to be able to do is we want these large language models to be able to reason over private information. And in order to do that, we want to take that private information and turn it into a semantic graph. So what we do with our reView platform is we have an API that you can call and load structured, unstructured, and time series data. What that does, the semantic encoder basically takes that information, and there's some techniques that we use to pull out the semantic information from the information itself, but we also label things. And I'll talk a little bit about the labeling on the next slide, but the result is a connected graph of ideas, people, and concepts. So that sits as basically a database. And then what we have is a person might ask a question. So here's kind of how the process works. A user will ask a question to our reasoner. Our reasoner will then go and take a look at that question and say, what are they talking about? What types of concepts? What type of people? And then it'll go and make a call to this connected knowledge graph and retrieve information that it thinks is valuable to be able to answer that question. We then take that information and we pass it to a large language model. The large language model will then process it with the question and the prompting that we give it to return an answer, and that answer we then return to the user. What's interesting about this is as that private data comes in, for example, we might bring in the name of an organization. Well, the public data might know a lot more about that organization. So it really marries all of this world knowledge with very local knowledge. And it's very important that these systems are trustworthy. In order to make sure that our system is trustworthy, we do everything available to us in order to make sure that the system is very difficult to go off the rails, so to speak. So for every node in our graph, every piece of evidence in our graph, we store a whole bunch of different information about it so that we can trace it back to the original system that it came from. We know where this data came from, what the usages are around the data, what the confidentiality is for the data. In fact, we actually implement the NIST 600 AI risk management framework so that we can make sure our application meets these standards and can reason over different pieces of information and include and exclude different pieces of information based on filtering, based on these parameters. And we also have an option to make our graph tamper-proof. And what we mean by that is we can take each node in the graph and we can create a hash for each node store that in the graph and sign it, and make sure that when we open that node later, that it is cryptographically signed and no one's modified anything on the node. It will slow the system down, but it's definitely a much, much higher level of standard that we can provide. We have also an integration with XQ Message, which really brings up our ability to provide secure transport of data into our system. And then once the data is in our system, we can use XQ to make sure we're reasoning over the correct security level of the information in the system. Okay, let's take a look at a use case of using the reView platform. So I wanted to design a use case that focused on cybersecurity and how we could reduce risk to critical infrastructure using linked data by reasoning over cyber intelligence and human intelligence. So I'll show you that in this demonstration. So really to build out this use case to motivate it, I wanted to position reView as a strategic defense tool that's integrating human intelligence with cyber intelligence. So in this first scenario, we're basically looking at a operative that collects some new intelligence on the ground in Afghanistan where the scenario takes place. And on this new piece of intelligence, there's an IP address and a malware endpoint kind of linking the two. And what we want to be able to do is we want to be able to add that information to the graph and basically understand the relevance of it. And it turns out this particular node connects some really important things together. But we want to be able to show how we can make that happen with this use case. And we want to be able to reason over this data set. So we want to be able to even find other pieces of infrastructure that might be affected by this new piece of intelligence. Maybe not directly, but they could be vulnerable because they're similar to the one that was initially infected. So we really want to show how we reason over these really different data sets. So let me talk a little bit about the data first. So there's really two data sets in this example. The first data set is we're looking at a use case that was developed by Ed Waltz at Patrick Henry College, and he's a professor of strategic intelligence there, focusing on targeting in this class. And he developed the first part of the data set that he allowed us to use for this purpose. And we, in the next data set, so that was the first one, that data set, I'll get into the details of it later, but what we did is we had to augment it with a cybersecurity angle. So Professor Waltz had his data set, we took his data and we turned that into input files in our system, we loaded it, and we generated a graph for his data set where we answered questions. And then what we did is we wrote our own narrative. We actually used generative AI to help me build some of the scenario out, but basically we built a data narrative of an attack, a cyber attack on a secure infrastructure. So we had to generate a secure infrastructure list and the whole scenario of basically an attack happening. So we loaded all that data in, and now we have the cyber scenario graph. And then what we do with our system, we can take these different scenarios and combine them. So we combine them into one knowledge graph, which is called the cybersecurity review, where we can ask questions over this data set and see how things are connected. And I'm going to give you a demonstration of the UI today. This is just a quick picture of it to give you a feel for what's going to happen in there. On the left side of the screen, there'll be a place where you can type in a question and get an answer, and it's going to base that answer on all of this information in the knowledge graph on the right. So the example here is an infrastructure facility called Bar Foo, and there's a bunch of critical servers in there. They're in red, a bunch of DMZ servers in there that are in blue. And we can sort of trace through the graph. There's this critical server here. It was talking to this DMZ server through this firewall, pointing to this malware endpoint, which was created by this group called Tech Savages that also created these other malware endpoints. And this is really how graphs work. You model how these things are connected. The note we're going to be looking at is this one here, and it really connects this gentleman, Hamad Darzi, with this IP server, and the server is connected to this critical infrastructure. And this is really this question and answer, and we want to be able to ask about this network of connections. So about the data set, the first data set, the one provided by Mr. Waltz, there's intelligence that basically covers an incident that happens in Afghanistan where an informant named Janak is killed. And there's all this information basically linking these different characters to the killing of Janak. So there's phone records, there's banking records, and then there's public normal intelligence. And then I've already talked about the data set we're using for the use case on the cyber side, but just to kind of explain how the malware works here, just to give you an idea of what the story is supposed to sound like. It's a bit contrived, but you'll get the idea. So the way the malware works is it first infects a help system. So this would be a system in the Barfouz Nuclear Command and Control, DMZ facility. And this is a help system. So it's basically, the idea here is this help system communicates to the outside world and the internal points inside the system. And this initial help system has been compromised by a malware endpoint. So it's communicating with a known malware endpoint. It's getting instructions from that malware endpoint, and then it's also communicating with an internal server, which is a nuclear command and control server that controls a water cooling system, and actuators that's being controlled by a SCADA controller subsystem. So we're basically controlling the system through the malware endpoint. And the data set we generated was a set of critical servers, network firewall traffic, both internal and external, with the various connections between the servers we need in order to make it work. Malware files, we used the stuff from the CVE NIST malware files, and then the infected endpoints and human intelligence data that we got from Mr. Walls. The National Vulnerability Database, that's what we used for the malware data. And here's just an example of it asking it a question. So after loading all this data in, this is the question we ask it. What is the significance of the human intelligence evidence we got off Hamad Darzi when we interviewed him about the death of Janak? I want you to tell me about what systems might be infected and what we should do to patch them. So this is the answer we were able to create based on all of that information we ingested. So first off, as you can see in the answer, it really starts, and we can change how the prompting on this works. This is just an example of how it could come back, but it starts out by addressing the infected systems. So it knows that this one here, a little bit more information about the node. It knows that this server has been flagged for hosting malware because of this note. And then we went and checked the firewall log data, and the system itself looked through the firewall log data and noticed that that server was going to a malware endpoint. It looked up the malware endpoint and it saw where it came from, what data was first found, what it actually does, that malware endpoint, and a little bit more information about it. It looks inside the graph. It also noticed that this server 767676 was commuting with that malware endpoint, so it looked in the internal firewall DMZ to find that. We didn't tell it to do this, it just did this because we provided all the data in the graph. It also looked at the connection here. It looks like there's another system that it was also talking to. There were two systems that were connected to this infected server that it found. And then it talks about the vulnerability that's associated with the malware endpoint. So it basically looks up the information about the CVE, so it understands that context. Goes on to talk about what's the patch recommendations are. So because it was able to isolate which machines were infected, which machines were talking to which machines, and it knows about the patch, it can really put together sort of a list of decent recommendations, at least on the first pass, around what you should be doing what systems you should be looking at and what things you should be doing to update the systems. You could ask it other questions like what machines has that IP address been talking to, and it'll come back with answers to those types of questions. It's probably easier just to show you a little bit about the system, so we're going to jump into a live demo now. So this is a system. It's pretty straightforward how it works. First, I'll show you the layout. First, on the left side of the screen, you're going to see basically where we set the system up for question answering. And then there's the right side of the screen, which is looking at all the evidence, like the human intelligence, the financial intelligence. So first, let's just set ourselves up. So in the system, you can have multiple graphs. This is just one graph we're looking at. So we've got a bunch of different clients right now that we're working with. We'll take a look at this Cyber Janak use case. And we'll pick it and we'll grab this experiment. Now we pick a model, what we want to use as our reasoner. And we can pick whatever model we've created here. Right now we'll go with GPT-4o. And what it's going to be doing is it's going to be using this as our reasoning engine. The next bit is it's selecting the reasoner clearance level. And I'll show you what that means at the data side maybe. If I click on these different sections here, each one of, like this is human intelligence and it's all security level secret. Financial intelligence is secret level. Signals intelligence is secret level. The critical servers, this is a bit different. So these are top secret servers. So when I'm reasoning, I want to be able to set my reasoner's clearance level to know how much information I can expose to the AI by filtering it against these different filters that we have. So we'll use this question, explain the significance of the note found on Darcy's computer and the risk to the critical infrastructure. So I'll just ask that question. That's going to run in the background. We can continue to work over here on the right side of the screen. So I'll just sort of show you the information we have in the system while it's looking to ask that. So if we go to human intelligence, this is all of that on the ground information. We're going to index this information on our graph against a whole bunch of different things like people, locations, different information that we're trying to understand. Then there's financial intelligence. This talks about all the bank transactions that occurred. Signals intelligence, phone numbers and records. Critical servers, this is a list of all of the internal servers that we consider critical and what they do. So this would basically be an inventory of critical servers and what's the importance of the server, because we want the AI to be able to reason over potentially, which one should be patched in what order. We need to have a way to keep track of what's more important than others. And then we've got DMZ servers. Okay, our answer came back on the left here. I'll just finish the walkthrough of the screen on the right first. And here's all the DMZ servers. So these are the servers that sit in the demilitarized zone that are talking internally and externally. Malware endpoints, this would be a list of known malware endpoints and their level of security clearance as well. Some may be more secure than others. And then we connect these malware endpoints back to its vulnerabilities. So here's really the malware story. Then we have an internal firewall log, an external firewall log, a knowledge model, and I'll show you what the knowledge model looks like. This is where we're actually looking at the structure for the first time of the graph that we're reasoning over. So you can see over here, we asked our question, explain the significance of the note found on Darcy's computer, and then it came back with an answer. So this was the note, and I'll show you what that note is in the system here because the graph came up. So we asked about, so here's Hamad Darcy, and there's these green notes, green things here. These are basically intelligence about him, human intelligence about Darcy. And you can see here, this is one of the early ones. This is where we're basically connecting Darcy to a couple bank accounts. But what's interesting here, this is the note. Let's just find it right here. Yeah. So this one here says, note retrieved from Darcy's computer from a hacker located at, then we have an address indicating a server located at 1.61.80.33 is listening to. So this is basically a piece of text evidence that we found on this subject, and we want to know what are the implications of it. So let's see what it has to say. So there's a malware endpoint. This server is connected to a malware endpoint that's part of a denial of service on a water treatment plant. Interesting. Okay, so let's take a look at this graph to see where it got that from. So here's the note, and here's that server. Let's just make this a bit bigger and expand it. And now we're going to be able to see for this server right here, all of the other things so we know this is a help system. It's an internal firewall. There's an internal firewall log for it. So there's all these different, like this server here was talking internally. Let's just expand this. Okay, here we go. So this machine here was talking on an internal firewall log to this one here, which is noticed as a critical server. So I'll just expand this, what kind of critical server it is. So now we can see this is a water treatment system. Okay, so we can really sort of follow this trail back. So what the reasoner is doing is it's looking at this graph and the connections in it, and it's using that to create this summary over here of what it understands about the situation. And there's a whole bunch of nuance that's going on in the graph. Like, for example, this machine here is that server in the demilitarized zone, and this is the Barfu facility. So this is that nuclear facility that has this critical server here. If I double click on it, we can see that, so it's a real-time monitoring, control, and alert systems for industrial cooling. So it's using these summaries over here about these servers when it's generating this text over here on the left. So it's really using this graph and the relationships to be able to understand how things connect to one another when it's generating these replies. And then see how it's quoting these node IDs here? And it references this node ID, which is a node ID right here. So you're able to connect where it's getting its information from with each ID of each one of these nodes. So you know that this piece of information wasn't hallucinated because it came from that spot. You can go and check it. So whenever it's making these statements, it's giving you information about where it's getting that information from. And that really helps us being able to trace all of this information and understand and that the reasoner is actually quoting its sources, its evidence, where it's making these decisions from. So that's kind of how we combine these two graphs with question answering. If I go back to the top here, inside the system, you can go and check things like, for example, let's say I want to know a little bit about more of this IP address. I can copy it. Now I could just ask another question, summarize that IP address, but I might want to check the source data as well. So I'm going to put that IP address up here, and I can just go through these different pieces of information and see, where else is this being mentioned. Okay, it looks like it wasn't being mentioned other than in 2 pieces of human intelligence. So there's 2 pieces of human intelligence here that are referencing that IP address. So if we were to summarize it, we could get it back a summary. But this is just sort of a quick search way to be able to look. Let's say you're interested in what's going on, something here. You may want to search for that information in any of these different data centers. So that's basically a quick overview of how the reView cybersecurity platform works. And thank you for watching.